In Module 6, we're going to be talking about secure coding practices for cryptography. You don't have to be an expert in cryptography. In fact, that's one of the beauty parts of .NET. It's all built in there for you. We'll talk about a little bit of cryptography you need to know, but mostly our focus is on how to just implement it. Now, of course, EC Council does have their Certified Encryption Specialist course if you'd like to have a more deep dive on how cryptography works. Our objectives are for you to primarily understand how cryptography works in .NET and then be able to at least explain the essentials of symmetric and asymmetric encryption and how we do defensive coding using both symmetric and asymmetric encryption. We'll also be explaining hashing and digital signatures, digital certificates, and again how you use those in .NET. Our focus is not on making you a cryptographer. There's not going to be any advanced mathematics here. We just want you to know what's available to you in .NET. Cryptography is all about securing information. We want to transform the information so that some intercepting party can't read what it says, but that the intended party can easily decode it and see what we meant them to see. There are code libraries that are built into .NET to do this for you. Encryption really comes into two different categories, symmetric versus asymmetric. Symmetric just means we're going to use the same key to encrypt that we use to decrypt. Now that may seem obvious. I mean, what else would you do? If I lock my house with a key, well, that same key unlocks it. Well, it's true that symmetric cryptography is easier to understand. It's also true that it's always as secure as the asymmetric, but with a smaller key, and it always works faster. But there's a problem. How do we exchange that key? You and I don't live in the same city. If you wanted to send me an encrypted email, there's no good way for me to get you a key for us to encrypt that email. This is where asymmetric cryptography comes in. There are actually two keys used. One will encrypt the message, but that same key will not decrypt it. Only another second different key will decrypt it. So I put that encrypting key out for the whole public. I don't care if everyone on the planet has a copy. If you encrypt a message to me using that public key and someone else intercepts it and tries to decrypt it, they won't be able to. They'll get out more gibberish. Only that second key that I keep private, my private key, will allow me to decrypt the message. So now I've taken care of that key exchange problem. You can send me messages at any time without us having to pre-exchange a key. That's the essential difference between symmetric and asymmetric. So first we look at modern ciphers and we break them down into a couple of different ways of looking at them. The first is asymmetric or symmetric, but symmetric can also be broken down further into either a block cipher or a stream cipher, and the names suggest exactly how they work. Block ciphers chop the plain text up into blocks of fixed sizes and encrypt each block. Stream ciphers encrypt continuous streams of data, but both block and stream ciphers are a type of symmetric. Now there are different modes to use with those block ciphers, and they have different purposes. We're going to look at these: the electronic codebook mode, cipher block chaining, which is my favorite, cipher feedback, output feedback, and ciphertext stealing. That's not really a mode, that's an attack mechanism. We'll look at those modes a little later, but let's first look at the key sizes. It's not enough just to have a really big key. If you have a really big key on a really bad algorithm, that won't help. It would be like putting a really, really serious deadbolt lock on a really flimsy door. It doesn't help. But if the algorithm is secure, then the longer the key, the better. DES used a 56-bit key, and again, it was published in 1976. That was plenty at the time. But eventually it was discovered that that wasn't secure enough. With more modern computers, it was possible to brute force crack that key. So there was a contest to find a replacement. Ultimately, what was selected was an algorithm developed by two Belgian cryptographers. The name comes from a fusion of their names, and it's the Rijndel cipher. That became the advanced encryption standard. It has three key sizes: 128, 192, and 256-bit. Now in the interim, while we were trying to find a replacement for DES, triple DES was used. You basically used 2 or 3 56-bit DES keys to encrypt 2 or 3 times. RC2 is an older stream cipher. It's been supplanted with RC4, but these are stream ciphers, and they have varied key lengths. Now, these are just a few algorithms. There are lots of other symmetric ciphers out there, Blowfish and Twofish and Serpent and Ghost, but these are the most common. What you'll normally see used is AES, probably more common than any other. Asymmetric algorithms are a little different. Now, what you're seeing on the screen here are simply examples of key sizes. As time goes on, we tend to use larger and larger key sizes. For example, RSA, the smallest key size you can get today is 2048-bit, and 4096-bit is more recommended. We have Diffie-Hellman, abbreviated DH. We have the digital signature algorithm, El-Gamal, and elliptic curve algorithms. Elliptic curve is a whole suite of algorithms based on a specific mathematical problem. Now, we can roughly compare the strength of a symmetric key to the strength of an asymmetric key. And this isn't exact. It will also depend on the algorithm, but this gives you an idea of what I was talking about earlier when I said that symmetric cryptography is always just as secure, but with a smaller key. So you can see here a rough estimate is a 128-bit symmetric key is roughly as strong as a 2304-bit asymmetric key. And again, that's just a general comparison. We'd have to get very specific about particular algorithms to be more exact. What do we use cryptography for? Confidentiality is the most obvious. I want to send you a message, and I only want you to see it. I don't want anyone else to see it. Integrity. I want to make sure the data wasn't messed with in transit. Non-repudiation. You want to prove who sent it. You're installing a new driver for your printer. You really want to make sure that driver came from the printer vendor and isn't really spyware. So we want to do non-repudiation. And cryptography is often used in authentication. Using encryption mitigates a lot of threats. For example, information disclosure. We don't want information to be disclosed to other parties. So we encrypt data in transit, we encrypt data at rest, that sort of thing. We don't want data to be tampered with. So we're going to use things like message authentication codes, hash message authentication codes, hashing algorithms, digital signatures, and similar ideas. We want to prevent spoofing. We want to authenticate the user. So we might use digital signatures and digital certificates to do that. Now, crypto, favorite topic of mine, but it alone isn't solving all of your security problems. We've already had several modules where we discussed a number of secure coding practices apart from cryptography, and that's intentional. Here's a quote. If you think crypto can solve the problem, you probably don't understand the problem. Crypto is only part of the security solution, an important part, but only part. There are a variety of cryptographic attacks wherein the attacker will try to intercept and decrypt the message. A lot of these depend on how effectively the encryption was implemented. Now, brute force attacks depend on an attacker trying every possible key to see what works. In modern algorithms, that's almost never effective. If you take 128-bit AES, the smallest AES key size you can use, that means there are 2 to the 128th power possible keys. If you were to try 1 trillion keys a second, the sun would burn out before you've tried all the possible keys. So that's not effective. Normally the way people crack encryption is not through breaking the algorithm, it's getting into the key exchange mechanism, seeing weaknesses in the implementation of the encryption. It's not the algorithm itself. Now, what are some techniques an attacker can use? Brute force we just discussed, that's unlikely to work. But theft of a key, if you're storing the key in an insecure way and I steal your key, well, that works. Identifying and exploiting weaknesses in the algorithm using cryptanalysis is far less common. It takes a huge amount of time and a lot of effort to really break an algorithm in this fashion. This is usually something researchers do over long periods of time. Looking for weaknesses in the software that implements the cryptographic solution, now that's a common way to do it. Perhaps you have used really strong encryption to encrypt your hard drive. But when you encrypt a hard drive, you have to give it a password. If you used a really bad password, well, I might guess your password. I never really broke your encryption, but I circumvented it. Using social engineering or blackmailing to get information from someone, to get their password, to get their key. Using what are called side channel attacks. Now, these are very obscure attacks, not likely to be usable by most people. They're looking for things like electromagnetic radiation from cryptographic devices, when key exchange occurs to attempt to derive information about the key. A very obscure attack, but it is possible. Getting physical access to the computer and getting key loggers. Now, a key logger logs your keystrokes, not your encryption key. But let's say you've encrypted some files. I can't break your encryption, but I get a key logger on your computer. When you type in the password to that file, well, now I have the password. I don't have to break your encryption. I can access it the same way you do. What are some general things we need to do to be secure against cryptographic attacks? This first one is the most important. Avoid implementing custom cryptography functions. Let me stress this. Lots of people, when they're new to cryptography, they learn a few algorithms, and they now believe that they can create their own encryption algorithm. It is almost guaranteed that you're going to make an algorithm that is far weaker than the ones already available. When encryption algorithms are designed, people with extensive mathematical training spend a great deal of time developing and testing their algorithm, and then they publish it. And immediately other cryptographers begin to analyze it, to look for weaknesses, to look for attacks. And after a period of years of this sort of intense review from the scientific community, then an algorithm is ready to be used in public. The odds of an amateur coming up with an algorithm that is not surprisingly and shockingly weak are almost nil. I say almost because it's not impossible, but why not just use the proven algorithms that are out there? Don't ever create your own cryptography. Using cryptographic services that are supplied by .NET will help you in this regard. They're already using the widely used algorithms like SHA-2 and AES and RSA and things that are already proven. Always select the strongest algorithm you can for the scenario. If you can use a stronger one and it doesn't impede usability, go with that. Always use the longest key that's appropriate. Now, I mentioned RSA keys getting larger and larger. That's because the smaller ones have been broken, but it takes a while to generate an RSA key. It's generated from some prime numbers and some calculations. So super large keys may not be practical. It takes too long to generate them, and then the algorithm is slower. But as long as you can use in a particular situation, that's the length you need, the longest that works in that scenario. When you're using symmetric keys, always have a good random number generator to generate a random cipher key. Shouldn't be any pattern to it. It should be as random as possible. Make sure if you're exchanging keys, you do so in a very secure manner. Particularly when you're giving out your public keys, you want to make sure that they're being contained in a digital certificate. That's the common way to do it, which gives some validation of whose key it is. Private keys must be stored in a secure place. Change keys periodically. If you're encrypting your hard drive and you've been using the same algorithm and the same key for a year, it's definitely time to consider decrypting the hard drive and re-encrypting it with a different key. Digitally signing anything, that helps improve the security of the entire situation. Using digital certificates, and even XML documents get encrypted or get signed with a digital signature. There are some namespaces built into .NET that have all of this there for you. The security.cryptography, the security.cryptography X509 certificate, and security.cryptography.xml. These are built into .NET, so again, you don't have to make your own encryption. You don't even really have to know how the algorithms work. You just have to know which ones to use. Now, the main namespace used is system.security.cryptography, and you can see on this slide it's broken down into sub-namespaces, which has symmetric and asymmetric algorithms. It has hashing algorithms. This goes back to use the strongest possible. For example, if you're going to use a symmetric algorithm, if at all possible, go with the Reindel cipher AES. If you're going to use asymmetric, usually RSA with the largest key you can. If you're going to use a hash, we always want, if possible, an HMAC, and whether we're using an HMAC or not, we want to use SHA with the largest key size possible. It's not really a key size in SHA, I should point that out. It's the size of output it puts out. There's not a key in a hash, but using the larger outputs will actually make it more secure. For example, SHA-512 is far less prone to collisions than SHA-256. Here we just see a set of classes available out there for DES, MD5, RSA, SHA-1, triple DES. All these are available to you within the .NET framework. Let's take a look at symmetric encryption in particular. Now we know that it's included within our security namespace. We know that we have AES and DES and RC2 and Reindel and triple DES. Now AES is in fact Reindel, but AES had some specific restrictions put on Reindel. The Reindel algorithm itself allows other key sizes, but the AES standard uses Reindel with only 128, 192, or 256 bit. What are some things you set? You set the block size, you set the key size, you can use an initialization vector, that's a random number that's fused with the key to make it even harder. You can set padding, you can create an instance of this class, you can encrypt and decrypt data, you can generate keys, you can check if it's a valid key size. All these methods are available to you in your symmetric algorithm class. So here we see a little bit of code. And what we're doing is we're using the Reindel cipher, and we're creating an encryptor so I can then encrypt any text I'd like to encrypt. And of course, we create the decryptor at the same time. I'll want to decrypt that text at some point. Defensive coding techniques using symmetric encryption. We look here, we have vulnerable versus secure code. And the bottom line is, on the left-hand side, we're using an older, weaker algorithm, DES. On the right-hand side, we're using a newer, more secure algorithm. There's actually no reason why you should use older algorithms, and we can assume that at some point, Microsoft will even deprecate those from their library altogether. But for now, just make sure you're using the most secure algorithm that you can in a given scenario. Now, we talked about modes earlier, and I didn't describe them. I said I would. Well, now I will. ECB, Electronic Codebook Mode. That's just a fancy way of saying use the algorithm the way it's written in all the textbooks with no sorts of modifications. There are some problems with that. Let's take a block cipher like AES. I divide my plain text into 128-bit blocks. What if, for some reason, 3 blocks in a row had the same text? I mean, 128 bits is not that much. It takes 8 bits to represent 1 character in ASCII code, so 128 bits is not that much. What if I happen to have the same word repeated 3 times for some reason? Well, if you think about this logically for a moment, if you take the same 128 bits, put it through the same algorithm using the same key, you're going to get the same ciphertext out. This leads to patterns appearing in the ciphertext that an attacker might use to attempt to start to circumvent your cryptography. Now, it's not an easy process for them to do this. It's quite difficult, in fact, but there's a possibility. Whenever possible, we don't want to use ECB mode. We have other modes that will help correct this problem. Now, here we see we're using ECB mode versus the secure code, which is CBC. What is CBC? Cipher block chaining. All that does is when you encrypt block A, you take the output of that, the ciphertext, and you exclusively OR it with the next block's plain text before you encrypt it. And you continue that chaining throughout the entire text. That way, you can have a text of millions of lines, and every 128 bits was identical. All the ciphertext would be different because of the cipher block chaining. Now, that's a concept you don't have to fully understand to use in .NET. Just make sure you always use CBC as opposed to ECB. Padding. You always have to pad your blocks because it's unlikely that they will appear as exact, precise block sizes. My message is not going to come out to exactly 128-bit blocks. The last block will need some sort of padding. How you pad it is important. You can use no padding, which is a bad idea. All zero padding, also a bad idea. But then we see three standards here. PKCS, that's the Public Key Cryptography Standard number 7 padding. ANSI X923 padding. And ISO standard 10126 padding. These are three different methods to pad at the end so that we don't reveal anything about the end of that block. Zero padding, well, the end will always look the same because it's always padded with zeros. So using the PKCS7 padding would be far more secure. And you can see we're changing one line of code here, so it's not a big effort on your part. Securing the encryption keys from brute force attacks. We come to the key size. AES 128-bit is pretty secure. But it doesn't take much to make it 256 bits, so why not use the more secure method? Many products today use AES 256-bit simply because it's far more secure. Resisting cryptanalysis attacks using large block size. Again, this is like key. It is not absolute. If you have a bad algorithm, a larger key or a larger block is not going to help you. But if you have a good algorithm, the larger key size and the larger the block size, the more secure the output will be. It's as simple as that. Creating non-predictable keys. There is a random number generator service provider built into .NET, and it will generate you random numbers. Now, this is different than the standard random number generator based on one simple fact. How random is random enough? If I'm generating a random number for, say, a card game, well, I expect to see patterns emerge. I expect to see people get 3 of a kind, get a pair, that sort of thing. If I'm generating a random number for cryptographic purposes, I don't want to see any patterns. So you can see on the left we're using the standard random number generator to get our key. But on the right, we're using the crypto service provider to generate a random number for our key. The right side is far more secure because your key is more random. How do we store the keys? Storing them in the registry is actually a pretty good idea because someone can't access the registry without administrative privileges to begin with. Storing them in a database is an issue, but then of course you have to encrypt them in the database, and now you have to store that key. Application configuration files, not such a good idea because those are easily accessible. Local files, again, you're going to have to encrypt that file or else it's accessible. And using things like the COM+ constructor key is really a bad idea. So what you're seeing here on this chart is a list from the best to the worst option for securely storing keys. Now you want to have access control list. I have this key and I put it, say, in the registry, but I don't want everyone to be able to access it. So we use access control lists that can be set manually or programmatically to allow only certain users to be able to access this key. And here we see some code for that. I've set up registry rights. I've changed permissions to deny access to a particular user for the registry key in the Windows registry that's storing my encryption key. There is an API called the DP API, which restricts access to Windows registry and to keys stored in there. You can take the registry key itself, and that's the place in the registry that you put your encryption key, and secure it with this API. And you can see that shown right here on this screen, which will help secure your key storage even more. Here we see how we would configure that, where we're going to store the user data. Are we going to use extra, what we call entropy or randomness, to encrypt with? What is the scope of this? These are options to allow us to be even more secure when we're storing a symmetric key in the Windows registry. Here's some sample code for protecting secret keys with the DP API, and you can see there's only a few lines of code here. This isn't particularly difficult, easy to implement, and you've now secured your key storage. Cryptographic applications. The cryptographic application should protect itself from cryptographic attacks. This should be obvious. So we use, first of all, the strong identity permission link demand. This is a way of ensuring that only certain people that are well authenticated can even access the cryptographic application. And we can see this done in code at the bottom of the screen you're seeing right now. This gives a public key, and we basically protect against someone attacking our cryptographic application itself. Encrypting data in the stream. We talked about stream ciphers. Now on the left, you have vulnerable code. On the right, we have secure code. And you can see that it was 5 lines of code added. And what we've done is we're using the encryption stream, using a key and an initialization vector to encrypt the entire stream that we're writing out. Now, streams are used with sockets programming. In this case, it is a TCP socket. They're also used with writing out to a file. Whatever the implementation, using the crypto stream actually encrypts that data as it's being written out in the stream. We talked about symmetric encryption. Let's talk about asymmetric. There's a class, as you might guess, for asymmetric algorithms. It includes Diffie-Hellman, elliptic curve versions of Diffie-Hellman, elliptic curve versions of DSA, and RSA. Again, elliptic curve is a class of algorithms, and there are variations of all the other algorithms accomplished with elliptic curves. And again, we can set some of the same properties, such as key size, but we also have key exchange algorithms, signature algorithm. Do we want to create a key? That sort of thing. Now here's a basic code sample, and as I told you throughout these lessons, we're going to give you lots of real code you can use. Here we've set up the RSA crypto service provider. And we're going to encrypt a particular piece of plain text, and we're also going to decrypt it all at the same place just to illustrate how that's done. Pretty simple, pretty straightforward. Let's look at some defensive coding techniques to use with asymmetric cryptography. First of all, key size is still an issue. On the left-hand side, they're using a 1024-bit RSA key. On the right-hand side is 2048-bit. We're back to the same issue, the largest key that's practical in your scenario. Storing the private keys securely. When you've generated the private key, it's obviously stored somewhere on your machine. But where should it be stored? Here you can see we've set up a key container, and we're actually storing our keys within that container. That's a much better way to store your private key. Asymmetric data padding. Like symmetric encryption, padding partial blocks help prevent certain attacks. Now these aren't really common attacks. They're difficult, but why not protect against them? It's pretty easy. .NET even supports one of the standard ways of asymmetric padding called optimal asymmetric encryption padding. Since it's supported, why not use it? You can see here, it's not even a line of code. It's one word. We change from false to true, and we have padding. Given how easy that is to implement, why would you not put that in to your code? Something we talked about in an earlier lesson, if we're going to send information back and forth, why not set SSL to true? That is apart from encrypting the individual data that we're encrypting. Let's go ahead and make the entire channel secure. And again, SSL in this day and age probably means TLS. Let's talk about cryptographic hashes. Now, we talked to you in one of the first lessons about confidentiality, integrity, and availability. So far, we've been discussing confidentiality, symmetric or asymmetric encryption to facilitate data confidentiality. Hashing is about integrity. Hashing, it's a cryptographic algorithm, but we're not really encrypting. What you're doing is you're taking data, you're putting it through an algorithm that will produce a fixed length output. For example, SHA-1's output is 160-bit. Doesn't matter if you put a single letter in there or you put thousands of pages in there, you get a 160-bit output. Nothing in hashing prevents any confidentiality attacks. What it does is help verify integrity. So if I send you a message, and at the end of the message I append a hash, when you receive the message, you can generate your own hash, compare it to the hash you received, and if anything got changed, you'll detect the difference. That's one of the uses of a hash. Now we'll see improvements on that in just a little while. Lots of hashing algorithms in there, MD5 and SHA-1, variations of SHA-2. There are also HMAC variations. Now we're going to talk in more detail in a little while about MACs and HMACs, but briefly, a hash message authentication code acknowledges one problem with the hash. What if someone intentionally intercepts my message, removes the hash at the end, alters the message, then generates their own hash? Well, using just a hash, that would check out on the other side. So what an HMAC does is, in addition to hashing, we exclusively OR that hash with some random number of the appropriate size that I have previously exchanged with the receiving party. Now, when he receives the message, he takes the hash, he hashes his message, also exclusively ORs that hash with this random number that we've exchanged, and compares them. Now, if an interceptor intercepts our message, removes our code at the end, and simply does the rehash, it's not going to match on the other end because the interceptor isn't even aware that we're using this extra number randomly generated to exclusively OR the hash, and even if they are aware, they don't have access to the number. So whenever possible, you'd like to use an HMAC as opposed to just a hash. In .NET, it's all in there for you. You don't have to understand the algorithms. You just have to use the right service provider. In this case, you can see the SHA-1 crypto service provider. So we pick a particular hash size, we pick the input and output block size, we create an instance of the class, and we compute a hash. You can use default values for all of these things like input and output block size if you like. Now here, we're doing a hash code on memory data. Now that's kind of interesting. We want to make sure that someone hasn't altered something in memory. So we take this message and we create a hash of it. And now anytime we like, we can create another hash and compare them and see if something was altered. Here we're doing the same thing only with stream data. We're opening up a file, and as we put it through, we're going to create an MD5 hash of it just so that we can later make sure nothing got changed. Now again, many of these examples will use a variety of hashes just to illustrate that they're available to you. MD5, SHA-1, things of that nature. But for your coding, whenever possible, use an HMAC, and whenever possible, use one of the larger output versions of SHA-2, like SHA-2, 256, or 512. You can use any size of message you want, and the hash is going to be of a fixed size. So that's not a problem. We already understand that. Doesn't matter the size, so that's not going to affect our hash. Two large messages create a hash code, but what's interesting is the slightest change will create a different hash. So when we're using these hashing algorithms, we're pretty confident that any change is going to be detected. Setting proper hash code length. Now it's a very, very obscure attack, but it is possible that extremely large messages might generate the same hash codes. It's almost never actually seen, but if you're concerned about that, you can set a limit of size for messages you're going to hash, and that's described on this particular slide. Here are the output lengths supported, and again, we're not too concerned with this. In general, message limits of 2 to the 64th power or 2 to the 128th power are extremely rare, so this probably won't even come up. But if you're using, for example, SHA-1 and your message is larger than 2 to the 64th power, you may encounter an issue with the security against collisions. And a collision simply means two different hashes were produced by two different inputs. In other words, I produce one input, I get a hash. I produce another input and I get the same hash. That's a collision. Extremely rare, unlikely to happen, but extremely large messages make this more likely. Using the keyed hashing algorithms, these are the message authentication codes, or HMACs, that I discussed before. This is a far more secure way of hashing, and whenever possible, you'd like to use an HMAC as opposed to a hash. And here we see it's not really a problem. I'm just using the keyed hash algorithm class, and when I create, I say I create an HMAC of SHA-1. So it's not any difficulty in coding. You don't even have to really understand the algorithms. Just bear in mind, whenever possible, use an HMAC. Now, digital signatures are an odd thing. They look odd to people at first because they're accomplishing a different goal in the CIA triangle. They're not concerned with confidentiality. By themselves, they do nothing for confidentiality. Now, don't worry, most secure messaging will include encryption for confidentiality, hashing or HMACs for integrity, and digital signatures to ensure non-repudiation, which is another aspect of integrity. The only thing a digital signature by itself is meant to do is to guarantee who sent this message. So essentially, we take asymmetric cryptography and flip it around. I sign something with my private key. Anybody who has my public key, and by definition that's pretty much anyone who wants it, can go in and verify my signature. And again, this provides no confidentiality. It's not meant to. It's just meant to prove who sent it. Here we're seeing the creation of a digital signature on the sender side, and the recipient receives it using my public key to verify that this is really my digital signature. So if, for example, you sent a message claiming to be me, you digitally sign it, but you don't have my private key, so you signed it with your private key. Someone who receives it thinks it comes from me, so they're going to try to verify it with my public key. Because it wasn't signed with my private key, it can't be verified with my public key. Now, there are two basic areas that an attacker can try to attack a digital signature. First of all, what is it we do with this private key? Normally, what we do is we hash the message and we encrypt that hash with our private key, and that is the digital signature. So the attacker may try to attack the underlying hash. This is incredibly unlikely. In fact, so unlikely as to be something you can dismiss from concern. The biggest problem is if my private key was not securely stored, someone can get it, and then they can digitally sign messages, and it will appear to be me, and it will be validated as if it were me. So the most important thing is keeping that private key well secured. Digital signatures basically make sure that if you don't have the private key, you can't create a signature. You can't fake it. You can't digitally sign messages. You can't alter the signed message because I've signed a hash, and that hash won't match on the other side. But also, the sender cannot deny that they sent the message. Since I have that private key and it's secure, it must have been me that sent it. That's what we mean when we say non-repudiation. Now, .NET contains a digital signature framework. You can see it right here. We're going to use RSA to digitally sign. We first create a hash of the message, and then we digitally sign that hash, and that's what we send. And we have the verify data method, you can see it right here on the screen, that will verify that signature. We are showing you this example again, only this time instead of RSA, we're using DSA, the digital signature algorithm. You can use just about any of the major asymmetric algorithms, but RSA and DSA are commonly used. What about digital certificates? First of all, I keep saying that you can distribute your public key to everyone. How do you do that? The most common way to do it is your public key is placed into a digital certificate. Now, certificates can be issued by a certificate authority, DigiCert, VeriSign, companies of that sort, or they can be self-signed. The problem with self-signed is no one can verify the certificate. So usually for secure communications, you're going to use third-party authenticated digital certificates. Here we see the standard contents that are used in a digital certificate. Now, if you look at very specific standards like the X509 standard, it'll get a little more detailed than this. But essentially, it has the public key, it has the digital signature of whoever issued this, and it has the algorithm they used to sign it, as well as validity information. X509 is the most standard way to do digital certificates, and guess what? .NET has an X509 certificate namespace built in, and it will allow you to generate X509 certificates right in your code. You can see right here, we say get a certificate from our certificate store. That gets us a digital certificate, an X509 certificate. Now, we've talked a lot about digital signatures and symmetric and asymmetric encryption, hashes, message authentication codes, and digital certificates. XML signatures are important. Why? Because XML data is frequently used on the internet for all kinds of communication. In fact, web services use XML to transmit data back and forth. So XML signatures are kind of important. The use of an XML file is very flexible. It's platform independent. It looks like tags, just like HTML, only it's displaying data. However, that flexibility also leads to some vulnerabilities. So securing the XML files using digital signatures. Using a signed XML class will verify who sent it. And remember, signatures are signing the hash. So we also verify that the XML data wasn't compromised. So you can use either just an XML class or the signed XML class. Here we're seeing source code that's going to take an XML file. It only has two pieces of data, a number and an expiration date for a credit card, but the code on the right shows us digitally signing that, and that makes sure that it wasn't tampered with in transit, and it also ensures who sent it. And here's the sample code continued. We can see the entire function provided for you where we're creating a signed XML document. Some specific secure cryptography practices used in ASP.NET Core. First of all, there's the Data Protection API, the DP API that we mentioned before. It's built in, and it gives you a lot of flexibility in securing things. For encryption, they suggest, and I agree, always use AES 256-bit in CBC mode for all symmetric encryption, and for hashing, use SHA-256 or even better, the HMAC version. And you can see the namespaces right here for password hashing, extensions for additional APIs, and other related APIs. Here we see some specific methods, like the create protector, the purpose string chaining, which allows us to create a chain of keys that are protecting other keys, essentially. Machine-wide policy. You can set a policy in the API that applies to an entire machine, for example, that requires CBC mode. That would be a good idea. Now, there are other modes, like the Galois counter mode, which is a little different and a little more complex. We don't really go into the depth of that in this particular course, but the CBC mode would be sufficient for almost all of your security needs. Key persistence. Do I want to be able to use this key again? Well, in most cases in cryptography you do. This is very different than cookie persistence. I want to keep that key and I want to save it to a particular location, and in this case we're protecting it with a digital certificate. How long is this key good for? Depends on the purpose. You might have a key that's good for a day. You might have a key that's good for a year. Depends on what you're encrypting, but make sure you've thought this through and you set the default key lifetime. The application name. Multiple applications may use the same key repository, so which keys does your application have access to? Well, that's based on the application name. So it's a good idea in the startup to set an internal name that's usable. This is interesting. In this case, it will not generate new keys automatically after expiration. You may or may not want to implement this. This says if a key expires, we need to go through the whole process to generate a new key. Don't automatically generate a new one. In many cases, this is going to be a much more secure option. Of course, remember that security and usability are always in conflict. What algorithm to use? Right here on the screen, we're seeing very simple code in startup that's going to determine that throughout this application, we're only going to use AES 256-bit with CBC cipher block chaining, and we're going to use an HMAC, a hash message authentication code on SHA-256, nothing else. This way, later in the code, someone can't choose a lesser algorithm. Now, this is particularly important in team programming environments. You want to make sure that another programmer doesn't use less robust cryptographic solutions. Here we have a random number generator creating a random string. Now again, notice we're using the random number generator class from the cryptography namespace. We talked about this earlier. This is far more secure than the standard random number generator. Here we can see a code example of hashing a string, and in this case, we're actually using, on the bottom example, we're using a specific algorithm, the HMAC SHA-512. So we're using a hash message authentication code with SHA-2 512 output. This is a much stronger way of hashing. Now at the top we see we're not doing this, but what's more important? What else are we doing here? In the bottom example you saw a single extra property called salt. Basically, salt is an algorithm that alters your input prior to hashing, and it's done to prevent rainbow table attacks we talked about earlier. Since salt is included here, it's usually a good idea, particularly if you're storing a password, to use salt. Storing all of your secrets in a secure place. Here we can see vulnerable code where we're just storing JSON files somewhere on our hard drive, and anyone could load those and read them. Here we're seeing a lot more secure method. We're using a secret protection method, and by secret we mean encrypted. We have a manager tool that stores various data on our local machine and protects and encrypts that sensitive data. So just by including the add user secrets at startup, we have added this to our application. There's also the Azure Key Vault. This has been included in Windows since Azure was first introduced. And here we have a key vault. We can see code, very brief amount of code to configure it, to generate a key, and to store it in the secure vault. Now in summary, this may be one of the more challenging modules because you may not know that much about cryptography algorithms, but that's actually the beauty part of what we're trying to explain. .NET handles the heavy lifting for you. Just understand which algorithms are more secure than others. Remember that cryptography can maintain confidentiality, integrity, and authenticity and non-repudiation. Make sure you understand the basic overview of symmetric, asymmetric, hashing, and digital signatures. Understand what the basic attacks are and how to defend against them. Most importantly, understand when using symmetric cryptography, try to go with AES 256-bit in CBC mode. When using hashes, use an HMAC, preferably with SHA-256 or 512. And always remember to use the largest key that's appropriate for your environment. These are a few of the most important items we covered in this module.